Okay, yeah, so then let me start. So, yeah, it's a great pleasure to speak at this conference. And I myself have been working on lattice gauge theory, for example. And in fact, I'm using the Bridge++ program, which appeared also in the talk. And I have been, most of this time in there is to generate the lattice gauge configurations uh, in the signals and etc. But let's see. But today I decided to talk about something different. Let's see about a little bit futuristic about quantum computers, and this work is in collaboration with the Sochigusa, which already appeared, and also work in progress with Christian Bauer. Now let's see. So okay, so hopefully it moves. It got stuck. Oh, yeah, here it is. Yes. Okay. So the big question is how to apply the quantum computers to high energy physics. And certainly it sounds like a potentially very promising subject because we got a large number of qubits already, several hundreds or so, and which is hard to simulate classically, at least naively. And it's going to be increasing the number of qubits, etc. But of course, we should always be careful because first of all, the qubits are very noisy, and even if you do something, there is no a priori no guarantee or proof, at least, that it's really you cannot simulate in classical computers. And also what's important for my purpose is that well, even if you wait 10 years, for example, the number of qubits is actually not that large actually. And if you want to try to simulate everything, for example, scattering all the very complicated particles in the standard model, etc., it's certainly not going to be enough. So what I want to do is to come up with some problem where there are some conditions are imposed. And one is that first of all, ideally the quantum effects are important, like a quantum interference, entanglement, etc. And well, there is no guarantee, no proof, but it sounds reasonable to assume that quantum systems are better suited for quantum simulations. Now, the second is that I want to have a small scale problem. I'm not going to solve everything. And I have a much smaller problem and focus on there and use a quantum computer there. And for other purposes, for many other purposes, classical computers are enough. Now, the third factor is that I want to start with some simplified model. Well, I'm a physicist by background, so I start with a simplified model and then try to include the complications one by one to approach the realistic model. And that's what I want to do when we want to apply the quantum technology to high energy physics. And one of the problems which might fit into this category is the Parton shower, so-called. Okay, so what's the Parton shower? Well, let's see. It's actually relevant for many of the things we observe in the colliders, etc. And then there are separation of different energy scales, which is involved here, which is relevant for effective usage, etc. Now, at the very high energy scales, like a TeV, etc., there might be a lot of new particles, etc. But there, QCD is asymptotically free. Which means that you can compute many things from perturbation theory. There are programs like mud graph, etc., which you can compute a matrix element perturbatively, even if there is a new physics. Now, on the other end is a very low energy scale when lot of quarks and quarks hadronize, etc. And that's a very non-perturbative process, but there are already a lot of experiment going on. So we have a phenomenological model which we know fits the things. And the thing in the middle is called a Parton shower. And here there is a line which reproduces the quark, for example. And then the gluons come out, and then the gluons pair create quarks, etc. And it's going to be a very complicated process. And in particular, this is not exactly the usual perturbation theory because there is enhancement from soft collinear regions. And so you have to be careful with reorganizing the perturbative structure. And of course, each of these regions have their own uncertainties. But when I talk with experts, they seem to be the opinion that Parton shower, there are uncertainties, and the Parton shower is becoming increasingly important. Now, how to approach this? Well, you can also, of course, do the actual standard model, but instead I start with some simplified model, which captures the essence of the problem. And that is to start with the photons, but not our photon, but some other photon. We call it a dark photon, and it's called I call it A prime. And then it couples the fermions, which is like a quark, but charged under the photon, not under SU3. And then the Lagrangian is simple. And the important thing is that for the reason which will become clear, we have multiple copies of the fermions. So in other words, there are flavors, which is greater than one. And so there are coefficients of diagonal, etc. But otherwise, it's a very simple Lagrangian. And this is a toy model in a sense, but it's actually one of the models which appears in the physics beyond the standard model. And so these are photons, and the fermions is the dark fermions, and it's part of the dark sector, including extending the dark matter. And there are some motivations. For example, if there is a dark photons, it mediates the interaction between dark matter, and it might alleviate some of the tensions, which is relevant for the core cast problem, for example, in the galactic center, for example. Okay, so that is the important point is that it's a simple model, and in some context, there is some motivation. Now, okay, so what type of phenomena do we expect? So this one is an example of what you might expect, and it's somewhat similar to what happens in the collider. So, and in fact, this might happen in the collider in some scenarios. So here, chi, again, dark fermion coming in, and then it emits this wavy line, which is this dark photon. So it emits dark photon, and then if it emits the dark photon, what happens to that depends on the scenario. But for example, it might decay to muons, for example. And in this picture, it's 5 dark photons emitted, which means that 10 different muons are generated, which is actually very dramatic effects. So, you know, in a collider, there are a lot of backgrounds, etc., but it's very rare to find 10 muon event. If you actually observe this. So people are interested in that type of scenario as a characteristic signal, which is very, very different from anything else in the particle colliders. And so there's some motivations. Now the question is that, okay, why any of these, the quantum computer is relevant for things like this? And of course, people have been interested in this for many years, and they already programs, for example, well-known program PCR, which has more than 5,000 citations, etc., and Harvick, Sharpa, etc. And then all these things, this conference about the computations, and they do the computations using classical Monte Carlo. And there is a complicated formula written here, but actually you don't need to read it, but the essential idea is very simple. So the thing is that here, there is a dark fermion, or fermion coming in, and then there is a probability of emitting a photon. And so basically you do the Monte Carlo with that probability. So it might be that the dark fermion is coming here and it doesn't emit the photon, or it may emit a photon. And that's governed by this probability, which is given by this R. And there is a simple formula for that. Well, it's a complicated formula, but and this artery-Parisi splitting kernel. And then there's also a little bit of information on kinematics, for example. So when it emits, how much energy does the new emitted photon carries away? That's a parameter, and you also have to sample that. But in any case, there is a classical algorithm. So it's not too different from waiting the nucleus to split the decay, etc. And the idea is simple. So you just wait and then using the Monte Carlo to simulate it. That is the standard algorithm, and that has been used certainly more than 1,000 times in the high energy physics literature. Now, what's wrong with that? Well, let's see. Actually, well, in the usual situation, there isn't too much of a problem with that. But in general, in the type of scenarios I'm considering, there is a fundamental problem. Okay, what is the fundamental problem? Well, whatever that is, it's a classical Monte Carlo. So it's a classical algorithm. For us, we know that, of course, our world is quantums. So not everything quantum can be described as classical. And the example for that is a quantum interference effect. And here I have here's a picture, and in the quantum mechanics you have to evaluate the absolute value square of the amplitude, and then there's a cross term. So what is the cross term between? So here there's a horizontal line, which is the fermions, and there's an index ijk, which represents the flavors. So there are different types of fermions, and they're labeled by ijk, etc. And here you start with I, go to k in the middle, and end up going to j. So there is a k in the intermediate stage. But now in the quantum mechanics, you have to talk about the interference effect between K and different J, so K and L, for example. And those are off-diagonal elements, which is very, very important to quantum mechanics. Now, well, of course, in some cases, classical quantum is reasonably close to classical, so this effect might be suppressed. And there are some arguments that might be the case in SU3, for example. But in general, this interference effect might be extremely important. And people have tried a little bit, but fundamentally, it's very difficult to capture any quantum interference effects in the classical Monte Carlo. It's actually surprising that, despite thousands of papers have been written about it, there is no systematic efforts to incorporate quantum interference effects. Now, okay, so how do you do that? And we are now writing a paper with a very, very complicated quantum circuit. But let's see, but it's always nice to start with something extremely simple, and this is the simplest circuit. And here we start with the one of the qubit, which is not the Q naught in the first in the top, and that specifies just which flavor it is. And here imagine that there are only two types of flavors, which is represented by qubit, up or down. Now I'm going to do the Parton shower with the 4 steps, and hence four more qubits. And first of all, we're going to do the rotations in the first step, and that's because so it specifies up and down, specifies the flavor. But that's not the basis where the gauge interaction is diagonal. So you have to mass matrix and the diagonal gauge matrix is not the same. So you have to do the rotation. That's the first matrix. Do the unitary rotation. Now, in the second step, and so depending on which flavor, you're going to do the emissions. But the emission probability is different depending on the different flavor types. So you're going to do different rotations. So there's a control operations, and you're going to do the rotations differently, and then going to repeat that 4 times. And then in the end result, you're going to measure whether the particle has been emitted or not, and you can count how many particles emitted. So this is the simplest ever quantum Parton shower algorithm, and it's actually the number of qubits, for example, is just proportional to the steps, for example. So it's actually very doable, and so this is one of the plots we have in a paper. And it's a too busy a picture, but the important thing is that these dots. So first of all, there is this black cross, and these are classical Monte Carlo results. And then there is a red dot, which is used with the computed with a Qiskit simulator. And then there are some important differences. And there are differences. And in general, if you compare the red dot with the black dot, in general, so the horizontal axis is the number of particles emitted. And when the number of particles emitted becomes large, you begin to see that the probability becomes a little bit larger due to quantum interference effects. So which means that the effects of multiple emissions is enhanced as that number of particles becomes large. For example, if it's a 10 emission, for example, 10 particle emission, that's enhanced. So 10 particle emission is a very rare event. But it's good. It's actually encouraging that that effect is enhanced because that's a very dramatic effect. And if you ever find it, it's going to be a very characteristic signal. And here it's a case of 2 flavors, but you can actually go to 4 flavors, etc., 4 flavors, 8 flavors, etc. And then this effect is going to be more and more enhanced. So this is the result, and what we are working on is actually to, first of all, this was the simplest circuit ever, and then we're going to make it more realistic, first of all, so the extra data we have is first of all the information of the kinematics. So these are emissions. So and then there is a parameter, how much percentage of the momentum, for example, is carried away by the photon emitted from the fermion, for example, and that's a parameter. And then we are not keeping track of this information in this current in the previous circuit, and because simply we are only counting the number of photons emitted. So that needs to be incorporated. Now, people have thought about that in the context of classical Monte Carlo, and it is a clever algorithm for that. And we are trying to merge that type of information of kinematic algorithm with the quantum circuits I presented. And that means that we're going to consider a hybrid of classical and quantum circuits. So the kinematical information basically keep track of with the classical circuits. Well, of course, classical CPUs are much better doing that, remembering numbers. And then as far as the quantum interference effect or whether the particle emission has happened or not, that part we are going to do with the quantum circuit, not too different from the one I said before. And so that's the separation of jobs in a sense. But of course, it's a little bit subtle because it's the question is whether we can separate really cleanly in between the two. Because if you try to do something, and then, for example, in the quantum set, things are entangled. For example, if you measure something that might be affected, etc. So it's a little bit non-trivial to see whether you can incorporate the quantum and the classical aspects. But that's what we are going to do, and we are close to finishing the paper. And then somewhat related to it, there is another thing which in the Monte Carlo literature, which is called a Beto algorithm, and also somewhat related with that, there is a mid-circuit measurement. So mid-circuit measurement is that whenever you want to, instead of waiting towards the end to do the measurement, you can do the measurement in between, and then you can use the qubit, for example, for other purposes, which helps to eliminate the number of qubits, for example. So by using this combination of techniques, we are trying to incorporate almost many of the ingredients which is already in the classical Monte Carlo literature, and then trying to reduce the number of qubits and the number of gates. Well, actually, the number of qubits is only linear in the time step itself, which is not too bad. But we're going to eliminate the number of the circuits. And the final thing I want to say is that so here I talked about specific Parton Shao algorithm in the high energy theory. Oh, let me finish. Okay. Well, actually, I spoke too fast. But in any case, yes. But one thing I can say is that there is a more general question, like of what happens when one tries to do Monte Carlo in a situation where quantum effects are important. So I'm sure that there are many situations in computational physics where people do the Monte Carlo. But Monte Carlo is of course a classical algorithm. So, but we know that versus quantum, sometimes you have to talk about the quantum interference effects combined with Monte Carlo. And I'm very curious to know if you might know any other problem of that type. So, and in those cases, I would expect that some variation of an algorithm will be of use. And yeah, so that's the type of the things I'm thinking about. And hopefully this is a kind of a small stepping stone towards the larger story of how to use the quantum computers and the technology to the problems high energy physics all the way to experiments. Thank you.